Everybody. Hello, everybody. This is for the course at University of New South Wales for Maths 2099 Linear Algebra. I'm going to go through the solution of question 22 in this video. It is about a vector space and their dimension. Now, the question here, find the basis of the following vector spaces, and we would like to find out their dimension. First, we have a vectors in R3 satisfying this condition, and we would like to find out a basis for it. There are other ways to do it, but it is very simple to do this way. Because you have a plane equation here, and we can write plane equation as in a parametric form, and we know that how to do it very well. And in that way, we will be able to write it down, this equation, this set as a parametric way. So it will be like a spanning set, and that will give us the basis of the space. So that's what I'm going to do now. I will write down, this is a plane, as the equation of the plane. This is why I call this set P, set of the vector satisfying this condition. And as we know, this notation is extremely important. Everybody must know this. This is a set, elements, and the condition. Okay, we would like to find out the parametric form of this plane. So first, you need to choose one of them and write it down as in terms of the others. For example, choose x1 and take the others on the other side. Then we will have x1 minus 3x2 plus 4x3. And in this view, in this perspective, what we do, actually, we are taking the x2 and x3 as a free variable, because x2 and x3 can be anything, but x1 depending on the x2, x3. So saying the x2, for example, lambda x3 is equal to mu, and lambda mu will be any real number, then we will be able to write down x1 minus 3 lambda plus 4 mu, x2 is lambda, x3 is mu. So this set will be the set of the vectors such that lambda times and the coefficients of the lambda in this equation, it is minus 1, 1, 0. So that's that vector. And the coefficients of mu, 4, 0, 1. That's 4, 0, 1. This is the parametric form of this plane. And if we looked at this as a set, we realize that P is a spanning set of these two vectors, and they are linearly independent, right? And that means that you have two vectors which spans your whole subspace, and they are linearly independent. They are the basis of your space. And the dimension is just 2 because you have two basis elements. So the dimension of any vector space is the number of the elements in your basis. Okay, this is just a reminding ourselves. We've done such equations before. We've done such questions before. Let's move on to the second part of this question. Here, in this case, we have a polynomial, set of all polynomials of degree smaller than or equal to 2. And satisfying these two conditions, P2 is equal to 0, or P minus 1 is equal, and P minus 1 is equal to 0. This and is extremely important, actually. S is a subspace. And basis for S, we would like to find out basis for S. We would like to find out the dimension of it. Let's try to understand this set and how we can observe this set. So this is the polynomials of degree less than or equal to 2. I'm just writing down in an open form. And that is an equation we have here. When we put t is equal to 2, we will have 0. So this is a t equal to 2 case. T square, which is 2 square. And this is the p minus 1 case. That's also 0. So t is equal to minus 1. T square will be 1. So we have two equations needs to be satisfied. These are the polynomials satisfying these two equations. The coefficients needs to satisfy these two equations. So we can solve these two equations in order to be able to understand our set S. So is we have two equations and three unknowns. Whatever the way you would like to solve, you can do it. You can substitute um, back and forwards. You can do that, or you can use the linear algebra to do it. This is easier for me. I just write it down the coefficient matrix, and we would like to find out the reduced row echelon form for this matrix. I don't need to write it down right-hand side because right-hand side is 0. Whatever I do in the row operations, that will not be affected. It is just a 0. So then I don't need to write it down this 0, 0 here. It is regard. I don't need to. It's just the writing extra bits of pieces is not necessary. So if we apply the row operations, we will be able to find this matrix. Well, what this matrix says is that this is a coefficient, and this is corresponds A0, this is corresponding A1. So in this case, A2 is a free variable. Let's say A2 is lambda. And then A0 will be from the first row, that will be A0, 0A1, 2A2 is equal to 0, which means A0 is equal to minus 2A2, but A2 is lambda, then this will be A0 minus 2 lambda. And the second row says that A1 plus A2 is equal to 0. So A1 is equal to minus A2, but A2 is lambda, so this is just minus lambda. So all the polynomials here will be in this format. A0 will be minus 2 lambda, A1 will be minus lambda, A2 will be lambda, and these are the coefficient, right? This is 1t squared. We have 1t squared. But it's exactly, so I'm writing down A0, A1, A2, whatever I found here into here. And instead of the condition, I have lambda running through the all real numbers. So this is exactly the spanning set of the polynomial because this is lambda times this polynomial, and the polynomial here minus 2 minus t plus t squared. So you have one polynomial only, and the s, by just multiplying with the any a scalar lambda throughout all R, you will be able to obtain whole set S, whole subspace S. That means that span by one vector, but by one polynomial. This means that the dimension of S is just 1. I think this is straightforward. Let's do the C part of the question 22. So this is, here we have polynomials of degree 2 less than or equal to 2. And this time condition is given by this way. So P1 plus P3 is equal to 0. Again, same question. We would like to find out the basis of S, and the dimension of S is whatever we are going to figure out. We will figure out what is the dimension of S. That's the question. So these are the polynomials of this kind, A0 plus A1t plus A2t squared. So what is this condition? This condition is basically, I'm just writing down here. So this calculation is coming from here. I'm calculating here. So P1 is when we put the t is equal to 1. P3 when we put the t is equal to 3. So this P1 plus P3 should be 0. So this equation here means this plus this is equal to 0. So if you figure it out, we will find out this condition. So this condition is this condition. So I figured out here and plugged it back. So this is another definition. This is exactly the S. This is another definition of S. And what this says, well, this is a like you have 3 parameters, and these 3 parameters, one of them is depending on the 2 others, because A0, A1, A2 could be any real number, and we can write it down one of them as dependent variable of the other 2. So that's what I'm doing here. So I can say A1 is lambda, A2 is mu. So I'm choosing A1 and A2 as the parameters. And I can write A0 in terms of lambda and mu, just taking the these 2 on the other side. and saying A1 is lambda, A2 is mu, then I will have A0 minus 2 lambda minus 5 mu. This is A1, this is A2. That's what it is. So this is this set S, this is a space S. I would like to find out the spanning set. I will. So just by rearranging this equation as lambda times a polynomial plus mu times a polynomial. So that's minus lambda minus 2 plus t. And the mu coefficient is minus 5t squared. And these two, this is the, so coefficient, some scalar times the polynomial plus another scalar times another polynomial. It means that this is the spanning set of this polynomial and this polynomial. So just from here to here, I'm using the definition of the spanning. And these two polynomials are linearly independent, obviously. There is no common factor. You cannot, this one is not a multiple of this one because we have t squared here. We have t, it is impossible, right? One of them is not a multiple of each other. So these two are linearly independent. And S is the spanning set of these two vectors, these two polynomials. It means that these two polynomials is a basis of our vectors of our subspace S. Since we have two vectors in the basis, the dimension is 2. I think that is done. Let's have a look at the last part of the question 22. Now, we in this case, the subspace that we are dealing with have matrices, 2 by 2 matrices, such that the trace is 0. We would like to find out the basis of the S, and we would like to find out the dimension of S. So S, I'm writing down 2 by 2 matrices more open, and to be able to understand how can I understand this set S. So the matrix is 2 by 2, A, B, C, D, and the trace of X means this plus this needs to be 0. This is the trace. Trace of a matrix means that you are adding on the diagonal elements for the square matrices, of course. Otherwise, it does not make sense. Right? For every square matrix, trace is defined as a sum of the diagonal entries. So the trace of this matrix will be this plus this. So this is just a definition of a trace. So this equation tells us that A is equal to, or D is equal to minus A. So it means that I will just put it in A, B, C, D, A, B, C running through the all real numbers. Here we have A, B, C, D running all the numbers. So we have 4 parameters here, but we have 3 parameters here. Actually, so S has 3 parameters. And this is a general knowledge. I'm just recalling our knowledge here. What is the standard basis for the 2 by 2 matrices? We call them EIJ. These are the standard bases. EIJ is the matrices such that you have 1 in the IJ entry and 0 elsewhere. This is you can generalize this standard basis definition for n by n matrices, and that will work again. So I will try to give a kind of a general description so you can expand your knowledge towards the n dimensions. So this means that in the, for example, E11 means that the position 1, 1 has 1 and zeros elsewhere in the matrix. E12 will have the 1, 2 position. You will have 1 in the position in the place 1, 2 and zeros elsewhere. Similarly, E21, you have 1 in the position 2, 1, second row, first column, and then 0 elsewhere. E22, you have 1 in the 2, 2 position here, and then zeros elsewhere. So this is the basis for M22. So we can think of the basis for this one, right? We are looking at this as a vector space, as a subspace, as a vector space. So what we want, a multiple of times is, right? So the basis of this will be these matrices clearly because I will be able to multiply this matrix by A, that will give me this position, and then this position given by this, a multiple of this matrix will give me this position. A multiple of this matrix will give me this position. So everything will be done. So it is clear that this is a basis for S, because really the positions gives you the basis elements, as we realized here. And this is a general fact about matrices. This is the standard basis for M22. It's basically saying that the position, taking the position, concentrating on the position of the entry, then of course we are thinking about the spanning set. It's a multiple of it. So it will give you the whole A, B, C, D, right? A, B, C, D. Spanning set, all of those will give you the whole M22. Spanning set of this one will give you the whole S. It means that this is a basis of S. You have 3 vectors. Of course, the dimension is 3. And it is obvious from here as well. We can directly say from here, because we have only 3 parameters. And this 3 parameter A, B, C run through the all real numbers. Only 3 parameters here, 3 variables there. It is dimension 3. I hope everything is clear. Thank you very much. See you in the next video.